Dear friends, this is the lecture number 2 of electromagnetism. In the previous lecture, we discussed about Bell-Savart law and its applications. Today, we discuss Ampere's Circuital law, the second law of this chapter given by Ampere. Ampere's Circuital law. Circuital law. So, in previous video, I have told you Bell-Savart law has a lot of similarity with Coulomb's law of electrostatic chapter, and also we discussed the similarities and dissimilarities. The same way, if you want to understand Ampere's Circuital law, you have to recall Gauss law. Gauss law in electrostatics. You all have remembered the Gauss law in electrostatics. So this Ampere's Circuital law has also a lot of similarity with Gauss law in electrostatics. I know you all have forget about the Gauss law, which we have discussed before some months. I am reminding you again the Gauss law in electrostatics. What was the law? The law was like this: electric flux linked with a closed surface is 1 by epsilon naught times charge enclosed by it. Or I can say the law is like this: the surface integral of electric field over a closed surface is 1 by epsilon naught times charge enclosed by the surface. I am writing the law. You see, the surface integral of the surface integration in physics we have three type of integration: line integration, surface integration, and volume integration. And this is valid for surface. When integration is done over a surface, then that is called surface integration. When the surface integral of electric field over a closed surface, this closed symbol we have given there, is equal to 1 by epsilon naught times charge enclosed. Q in means charge enclosed by the surface. Ampere's Circuital law exactly same as this Gauss law. You see how it is same? It was about electric field, electrostatic chapter, but now we are in electromagnetism chapter. So we'll take obviously magnetic field. Ampere's Circuital law, just I am writing, you see, this is also integral, but it's not surface integral. It's a line integral. It is applied over a closed surface, but it is applied over a closed loop. Closed loop. It's line integration. Here the closed surface is called as a Gaussian surface, and here the closed loop on which we apply, that loop will be called as Amperian loop. Gaussian surface, Amperian loop. And you see, this is the closed, also this is closed, but this is surface, but this is line. Here is electric field and here is magnetic field. And here is surface integral, here it is line integral. Line integral of magnetic field over a closed loop. Same thing. Surface integral of electric field, line integral of magnetic field over a closed surface, over a closed loop is equal to, here 1 by epsilon naught times, and here it is mu naught times. Epsilon has the practice always it remain in denominator and mu naught remain in numerator. If epsilon naught remain in numerator, mu naught remain in denominator. Okay, they remain like this. So you know the constant in Coulomb's law 1 by 4 pi epsilon naught, but the constant in Bell-Savart law is mu naught by 4 pi. It is in denominator, it is in numerator. Okay, they always remain like this. This is experimentally. So now mu naught times, just like your 1 by epsilon naught times, it is mu naught times. Here it is charge enclosed and here partly enclosed. Here charge enclosed. Charge is the source of electric field. Charge is the source of electric field. But here who is the source of magnetic field? Current. Current is the source of magnetic field. So that is I in. Current enclosed by the loop. I am telling you the complete sentence. Line integral of magnetic field over a closed loop is equal to mu naught times current enclosed by the loop. Current enclosed by the loop. Also we can prove it. We can prove this one. Now you forget this Gauss law. Now your concentration is here. You see, you try to understand actually what is this fact. This is the current carrying conductor. One infinite current carrying conductor, you see, around it magnetic field exists. Around the conductor magnetic field exists where for a straight conductor magnetic field lines will be in which direction? Like this. For a straight conductor magnetic field lines, if this is the straight conductor, okay, by right hand thumb rule, you have done also this one in class 10th. You have done this one in class 10th, that straight conductor current pass through along the thumb, then the magnetic lines of process direction is like this. Okay, so the magnetic lines of process will be there. Magnetic field exists around it, but you enclose a loop. You consider a loop. Now I choose a loop here. You see, this is the loop. I choose one loop here. The loop direction I am taking like this. This side inward and this side outward. This side inward and this side outward. Inward symbol is like this and outward. Anywhere I will do like this. This is perpendicular to the plane inward, and anywhere I will do like this. This is perpendicular to the plane outward. This is the symbolic presentation of these two vectors. This is inward and this is outward. Remember. So here I choose a Amperian loop like this. On this loop we will apply Ampere's circuital law. And let's prove whether this RHS is coming or not by doing the integration of LHS. Magnetic field, this Amperian loop, radius you take, you can take the radius, suppose I take the radius as smaller. What is the magnetic field value at a distance r? For this loop I am going to prove it. What is the magnetic field value at a distance r? That magnetic field is determined by Bad-Savart law for a straight conductor. For a straight conductor using Bad-Savart law, though that the derivation is not in CBSE syllabus, but you can remember only the formula from Bad-Savart law. For infinite straight conductor magnetic field is mu naught I by 2 pi r. This is the magnetic field. And where is the direction of magnetic field? If this is the conductor, you have to keep the thumb like this. For a straight conductor, see how the direction of magnetic field will guide. This is the thumb here. If thumb is here, so in here the magnetic field will be inward. For every point at this side, magnetic field will be inward. For every point at this side, magnetic field will be inward. And for every point at this side, see, my fingers will enter into the whiteboard. Then holding this, just moving around this wire, again it will come out. My fingers will enter into the whiteboard this side, and again moving around this wire will come out like this. So here for any point magnetic field direction will be outward. But this is the direction in which I choose the loop. This is the direction in which I choose the loop. I am changing it to blue color. Okay. This black color is the direction of magnetic field, and the blue color I just choose the loop in that direction. I is the current passing through this conductor. I think you are clear. At a distance r, magnetic field exists everywhere. but at a distance r, this is the expression of magnetic field. And where is the direction of magnetic field? At this side it is inward, right hand thumb rule, and at this side it is outward. And this is the direction of loop I choose, and loop direction I am showing by blue color marker. Okay, I choose the loop, this side inward and this side outward. Loop is like this. Let's do the integration over this closed loop. B dot dl. B dot dl. So here magnetic field is inward. Also if you consider a dl, small element here, if you consider, also that small element dl vector will be tangent to it. Dl vector will be tangent inward. Okay, so if dl vector is tangent and direction is inward, so the angle between B and dl is 0. So this is B dl cos 0. So B is constant everywhere on the Amperian loop. B is constant. So B is taken to outside. Only integration of dl. And what is the integration of dl? 2 pi r. The whole circumference of the Amperian loop, 2 pi r. And if we put the value of B here, mu naught I divided by 2 pi r into 2 pi r, 2 pi r cancel, and you will get B mu naught r. You will get B dot dl. You will get B vector dot dl vector mu naught I. So RHS is coming mu naught I. Mu naught I means that I is enclosed by the Amperian loop. Is it proof now? See the proof. And this expression is brought from Bayes-Savart law. Also, this same expression we can derive using Ampere's circuital law. We will do that in the applications of Ampere's circuital law. But this expression is brought from Bayes-Savart law. Using Bayes-Savart law, we brought this expression and used this, and we proved Ampere's circuital law. Then Ampere's circuital law is 100% correct. You have no problem. Okay, now let's discuss about this current enclosed. Here total current I enclosed. Let's be more clear about this current enclosed by a loop. Suppose I will tell you one loop, you see. This is a loop. Try to understand clearly. So this is the current going out. Again the same current is coming like this, down. I current going up, again I current is coming down. Same wire, same current, and you choose the Amperian loop like this. This is your Amperian loop. Now if I will tell you to use Ampere's circuital law here, you see, now you will be more clear about the current enclosed. Current is going up, I current is coming down. What is the total current enclosed by this Amperian loop? How many times that current passed? 2 times, but in opposite direction. If one current is taken as a positive, then the other current is taken as negative. So here I minus I net current is 0. So mu naught into 0. Net current enclosed is equal to 0 by this loop. I hope now you become more clear about the current enclosed by the loop. Next we see again we will be more clear about this current enclosed. I am telling you one other thing. You see, this current, suppose you see, now I am changing the figure a little. This current now is passing like this. Enter inside it. Enter. Again outside the loop it pass. Again enter. You see? If I tell you to use Ampere's circuital law here, now you tell me the answer. Now you tell me the answer. B dot dl mu naught into how much? Pause the video here. See the answer. Then when you write the answer, you check whether you are right or wrong. How many times that current pass? This is a loop. The loop is not extended to this side. Current comes downward this side. But there is no loop. Loop is only here. How many times your current pass? 1, 2, 3. 3 times may be the same current, but you will see how many times it pass. Try to understand that one. 3 times pass means you have to take 3I, and all are in the same direction. Simple addition. So it is 3I. I hope you could be able to understand about the current enclosed by the ampere loop, as you also understood the charge enclosed by Gaussian surface in first chapter. So now next is we'll discuss the applications of Ampere's circuital law. What are the applications of Ampere's circuital law? Always comes in exam. So first we will go to application 1. Application 1. It's a thick conductor. Thick conductor. Infinite. Thick infinite conductor. Length is infinite. Thick infinite conductor means its thickness matters, its radius matters. Generally, when you think about conductor, immediately it comes to our mind it's a very narrow thing in which current pass. But no, here we'll discuss the thickness. Its cross section of the conductor matters for us. You see, I'm drawing the figure. So this is the conductor, very thick conductor. See, this is a thick conductor. Okay, through this thick conductor, current pass throughout the cross section. Its radius is R. Capital R is the radius, and the current I pass. I am not giving any arrow because current pass in the whole cross section of the conductor. Through the whole cross section of the conductor, current pass. Okay, we'll find magnetic field. We'll find magnetic field. We'll discuss 3 cases here: inside, outside, and on the conductor. It's a very important application of Ampere's circuital law, which is written as an example in your NCERT book. But it is important, very important, and also very easy. Just like your Gauss law application, spherical cell. How many cases you have done there? 3 cases. You have done one graph at last. Here is also one graph. Everything is the same, just like the Gauss law. Everything also, the derivation is also same, just like Gauss law. Now you see, I current passes through the cross section. R is equal to radius. I is a current passes through the whole cross section of the conductor. And thick conductor derivation is done by Ampere's circuital law. But thin conductor means for narrow conductor and outside point we can do by Bhatt-Savart law, which derivation is not in CBSE syllabus. Okay, so but we can do thick conductor by Ampere's circuital law. So now this is the axis of the conductor. The middle line is the axis of the conductor. Okay, now first do the case 1 where point lies inside, point P lies inside. See, this is the point P, it lies inside. If you want to find out at point P, we have to draw one Amperian loop to apply Ampere's circuital law. To apply Ampere's circuital law, we have to first draw one Amperian loop. This is the Amperian loop, and this point is at a distance of smaller from the axis of the conductor. At a distance of smaller from the axis. Now see, what is the, now we use Ampere's circuital law to find the expression of magnetic field there. We are interested to find the magnetic field there, so now we use Ampere's circuital law. So Amperian loop is clear to all of you. Point P is clear at a distance R, where small r is less than capital R. We find at point P where small r is less than capital R. Now using Ampere's circuital law on the loop, B dot dl mu naught, this is I in. In means how much current is enclosed by the loop. Through the whole conductor I current pass, but not matters for us. For us what matters here? how much current passes through this blue color loop, because that is our Amperian loop now. Try to understand. I current passes through the whole cross section, but that is not matter for us. We need the current which passes through this blue color loop, because that is our Amperian loop. So here B dl cos 0, how I have proved it, always B vector and dl vector for circular loop will be in the same direction, because B is tangent as well as dl is also tangent. So mu naught, but what is I enclosed by this small loop, how will find? By unitary method. How by unitary method? You see, the whole cross section is pi r square. The whole current passes I. In the whole cross section, I current pass, and in cross section, this small cross section, how much current pass? I in is equal to I by pi r square into pi r square. Unitary method. I hope you understand this unitary method. Pi cancel, so I in is this much. Pi r square by r square. So implies that B is taken to outside. Integration over dl. dl integration is always done over the Amperian loop, as you have done in Gauss law over Gaussian surface. Always Gaussian surface radius is taken in the integration. Similarly here, always Amperian loop radius is taken in the integration. Circumference means 2 pi small r, because it is always done over Amperian loop. Don't confuse in small r and capital. Capital R is the radius of the conductor, but here we will take small r as the integration is over Amperian loop. So mu naught I r square by r square. So B is equal to, now you see 1 r cancel here, mu naught I r divided by 2 pi r square. This is the expression of magnetic field inside the conductor, which can be derived only by using Ampere's Circuital law. So, but you mark how this B depends on R. It will go from the axis gradually towards the surface of the conductor. After some time, this small r will be equal to capital R. This small r will increase. If I take the P point here, I will take the P point here. So, if small r increase, what happens to the magnetic field? You see this relation. How B depends on R. All these are constants. B directly proportional to R. So inside the conductor, thick conductor, magnetic field is directly proportional to R, distance from the axis of the conductor. Now let's come outside. Case 2 I am doing here, that is outside. Outside we will discuss now. For that we have to choose one point here, which is again at a distance smaller, but here smaller is greater than capital R. We have to choose one Amperian loop. This is the Amperian loop I choose. This is your conductor. This is the Amperian loop I choose. Okay. So if this is the Amperian loop, now use Ampere's Circuital law. B vector dot dl vector mu naught I in, then B dl, the angle is 0 cos 0 integration mu naught, what is the value of I in? Through this Amperian loop, the whole I current pass. Can you able to see the figure? The whole I current pass, so this is I. So now B dl integration is 2 pi r Amperian loop to small r mu naught I. Then what is the expression of B? Mu naught I divided by 2 pi r. This is the magnetic field for outside the conductor. How B depends on R? Small r. For outside the conductor, B inversely proportional to small r. For inside the conductor, B directly proportional to small r. For outside the conductor, B inversely proportional to small r. Now let's see on the surface of the conductor. If I choose on the surface of the conductor, suppose the point is here. Here the point P on the surface of conductor. So its ampere loop will be the cross section of the conductor itself, means small r is equal to capital R. So you can write this expression directly. Case 3, on the surface of the conductor small r equal to capital R. You can directly put here, or you can write this one changing only the small r into capital R. You can write the whole this step, changing only small r equal to capital R. So it will come unit I by 2 pi r. Also you can put here. You can put here small r equal to capital R. Also you get the same expression. You can put in case 1. You can put in case 2 in place of small r capital R. If you put, you will get the expression, and this is maximum. On the surface of the conductor, magnetic field is maximum when current passes through it. So this is about the application 1, that is the magnetic field due to thick conductor. We discussed its 3 special cases. At last, we will not leave the graph because graph is 1 mark. We will not leave the graph. How will draw the graph? This is R from the axis of the conductor, distance from axis. This is magnetic field. Let's take a point that is the surface of the conductor, R equal to R. On the surface, magnetic field is maximum. Here magnetic field is maximum. Then this is on the surface. If we go towards this side means inside, this side means outside. This is inside, this is outside. Outside the conductor graph is like this, inversely proportional graph, and inside the conductor graph is like this. And this one you can write, this is the maximum value, mu naught I. This one maximum value, mu naught I by 2 pi r. You can write here r less than r, here r greater than r. And this one you can join by dotted line. Full 1 mark you will get. You will draw this graph. This counts as a 5 marks derivation in exams. How? State Ampere circuital law. 1 mark. 3 cases, 3 mark. Graph, 1 mark. Total become how much mark? 5 mark derivation. It always comes in exam. So this is the application number 2 of Ampere circuital law. Now we go to application number. This is the application number 1 of Ampere circuital law. Application number 1 of Ampere circuital law. Now we will go to application number 2. Application 2 of SCL. What is this application? Solenoid. We will do this for solenoid. Have you seen solenoid? Have you seen it? If you have not seen it practically, but you have seen solenoid-like substance. What is solenoid-like substance? You have seen spring used in your ballpoint pen, spring. Okay, one pen comes with a spring that you do like this, tick tock, tick tock. That spring, that is just the mini version of the solenoid. But in solenoid, the length is very large in comparison to its radius. What is the actual definition of solenoid? A conductor owned in the form of a helix. A conductor owned in the form of a helix where length is very large in comparison to radius. Then that is called solenoid. See, this is solenoid. Just looking like your spring. So this is the solenoid. And when you provide current to this solenoid, it behaves like a magnet, because current carrying conductor behaves like a magnet. And remember, inside the solenoid, magnetic field is uniform. Inside the solenoid, magnetic field is uniform. How magnetic field is uniform and why magnetic field is uniform? Let's discuss. I am telling you first about only one coil. This is one coil where current passes like this. Current passes with one coil, current moves like this. Where is the direction of magnetic field? You know, if current moves enter into the whiteboard, magnetic field along the thumb. For circular coil, How will know the direction of magnetic field? So if current enters like this, the thumb is the direction of magnetic field. So this is the direction of magnetic field. And other lines of forces will be curved like this. You have drawn also this pattern of lines of forces in lower classes. For a circular coil, magnetic lines of forces are like this. Only one line straight at the center, others line will be little curved. I am drawing another circular coil just above it. You see, this is another circular coil. Also same direction current pass. Also its magnetic field will be in that direction. See, magnetic field will be in that direction. Now let us draw another circular coil. I am drawing here another circular coil, or I can draw it here, another circular coil. Magnetic field here also current same direction. Magnetic field will be like this, and this magnetic field will be curved. So now you see here the middle line coincide, blue, black, blue, red. They now coincide and it become a continuous line, straight line. But what about other lines? This line actually curved. This is curved. This is curved. But when they now combine this lines of force with this lines of force with this lines of force, this curved lines, when these circular coils will be close to each other, what happens to these lines? When they combine, ultimately they will be also straight line. Means these lines also will be straight line. I am drawing now. See here, these lines also will be straight. These lines also will be straight. So inside the solenoid, magnetic lines of forces are straight line parallel to each other. That means inside the solenoid magnetic field is uniform. Similar to which device you have read in the second chapter? Capacitor. In capacitor, what is uniform? Inside the capacitor, electric field. Have you remembered? In capacitor, the electric field lines are parallel. In capacitor is the example of uniform electric field inside it, and solenoid uniform magnetic field inside it. But outside the solenoid, magnetic field is 0. Outside the capacitor, electric field is 0. Same thing, just a similar device. I always tell capacitor and inductor, they are just like two sisters. They are just like two sisters. Also you see, it's actually other name of this solenoid is inductor. That one we will discuss in after this chapter. Its other name is actually inductor. Its name capacitor, its name inductor. You see also the similarity in names. Capacitor, last OR. Inductor, last also OR. They are just like two sisters, much more similarity. But you play the role in electrostatics and you play the role in magnetism. Magnetic field is uniform, electric field is uniform. Outside electric field is 0, outside magnetic field will be 0. How magnetic field will be 0? When this line will be straight. And the straight line, you know, in magnet what happens? The line, this is north pole, this is south pole. Lines of forces pass from north to south. Again they pass inside the magnet from south to north. Because magnetic lines of forces always form closed loop. Closed loop. Unlike electric lines of forces. Electric lines of forces never form closed loop. But magnetic lines of forces form closed loop. Okay? Magnetic lines of forces form closed loop. So, here, if they form closed loop, this straight line, when will form the closed loop? To form closed loop, this straight line will pass like this. Outside, it will pass like this, will be in. The straight form straight line outside, just outside the solenoid, it will be in. To form closed loop. To form closed loop, it will be like this. But very close to the solenoid, no lines of forces will pass just outside the solenoid here. Okay, it will form closed loop, but how it will form closed loop? It will bend, but just outside it, no magnetic field will be here. no lines of force, so no magnetic field. So just outside the solenoid, magnetic field is equal to 0. This curve can't able to close now here because it passes in this direction. To be closed, it has to pass, it has to come like this. But here the effect will, here no effect will be here. Only little bending at this sides, and at this side little bending, and no effect. No effect will be because this is infinite distance. They will come from infinite like this, and here no magnetic field, no lines of force. So you remember, inside the solenoid magnetic field is uniform, and outside the solenoid, just outside it, magnetic field is 0. But this solenoid I can present symbolically. You see, this solenoid I can present it symbolically. How? Now see here, I am presenting it symbolically. So this is the line. So symbolically I am presenting it. Here the wire comes out. Here the wire enter, means dot symbol. Here the wire comes out. Here the wire enter. Cross means the current comes out, but dot means current enters inside. Symbolic presentation of this solenoid. I can also draw this solenoid like this, then it will be more clear to you. You see, I am taking suppose any core I am drawing the solenoid. I am taking one core. You see the lines of forces, the current comes out and enter. Out and enter means current comes out here and enter inside it. So this is the practical diagram of the solenoid. Okay, practical diagram of the solenoid. Current comes out, symbolically I present it like this. Current comes out and enter. This is actual figure, and this is actual 3D figure, and this is the symbolic presentation. Okay, now we are interested to find the magnetic field inside the solenoid, because outside the solenoid magnetic field is 0, nothing to find out. It is the application number 2. How will find? If current now comes out and enter like this, magnetic, now current enter. Where is the direction of magnetic field? Now is it clear? So this is the direction of magnetic field. This is the direction of magnetic field. See. Right hand is everything for you here. Current comes out and enter. This is the direction of the magnetic field here. Okay, to find the magnetic field inside, we have to choose an Amperian loop. How we will choose the Amperian loop? According to how the derivation will be easy, accordingly we will choose the Amperian loop. Let's choose one Amperian loop like this. I choose one rectangular Amperian loop of length here. So I choose a rectangular Amperian loop. You see A, B, C, D, A. Amperian loop will go like this in this loop. A to B, B to C, C to D, D to A. Okay. So Amperian loop of length L. And how many total turns are enclosed by this loop? Because that is important. How many total turns are enclosed? If you see the actual figure, 1, 2, 3. In 3 turns, now current enters inside the loop. Can you able to mark? Because that is important. Current enclosed by the loop is important for us. 3 turns, current enters inside the loop. Okay? I is the current passes through each turn, and L is equal to length of the Amperian loop. Capital N will not take as 3 turns enter, we will take n number of turns enter. Capital N number of turns enter into the loop now of length L. Okay, in the rectangular loop, ABCD is the rectangular loop, capital N number of turns enter. So what is the number of turns per unit length? Capital N number of turns present in L length. So I take N by L is small n. Okay, small n is number of turns per unit length. Now let's apply Ampere's circuital law. It's a very easy derivation. B dot dl mu naught I in, and split this integration into 3 parts, 4 parts. Now it will be A to B, B dot dl, then B to C, B dot dl, then C to D, B dot dl, then d to a, then v dot dl, then mu naught. What is the current enclosed? How many times? N times. Not 3, don't keep in mind 3. I have told you n times. N number of terms inside it. So this is Ni. Current enclosed is equal to Ni. Number of terms into I. Now is equal to, you see magnetic field and dl for AB is in same direction. So this one, no closed symbol here. You see. Why no closed symbol? Because this closed loop is split into 4 parts. So no more closed symbol. So here B dl cos 0, because angle is 0 here. For BC it is 90 degree. So this one B dl cos 90, and this one C to D. This is B dl cos. Here magnetic field is like this in this direction. You are going from C to D cos 180. And here B dot dl, B dl cos again 90. For this one it's a 90. So mu naught n r. Now understand this one, the angles what I put. I hope everybody understood or not. Clearly you will see I have done one mistake. Knowingly I have done one mistake. Now you pause the video here and point out my mistake where I have done the mistake. Pause the video and point out the mistake. Then again you play it so that you can be able to know, you can be able to test your own brain. Okay? So where I have done the mistake? This one, how you know the angle as 180? Outside the solenoid, is there any magnetic field? Outside the solenoid, here magnetic field is equal to 0. How you know the direction of magnetic field where there is no magnetic field? So this is not angle 0. This is completely 0, not angle 180. Completely 0 because magnetic field is 0 from C to D. Don't write 180. Okay? So this one 0 cos 90. This is cos 90 0. Now what comes here? B constant taken to outside. This dl integration over AB is nothing but L mu naught Ni. So B is equal to mu naught Ni by L. So it is coming mu naught small Ni. So this is the magnetic field over magnetic field inside the solenoid, which is uniform constant magnetic field inside the solenoid. But if you come to the end of the solenoid, exactly no derivation for the end of the solenoid is there for you, for your level. But you can see if you come to the end of the solenoid, end means it's just average of inside and outside. And outside magnetic field is 0 and inside magnetic field is mu naught Ni, mu naught small Ni. So its average will take, so it becomes a half mu naught Ni. So it is told that outside the solenoid, at the end of the solenoid, outside means not to this side and this side, at the end of the solenoid, just at the end of the solenoid, magnetic field becomes a half. Magnetic field becomes a half. If you draw a graph of this for magnetic field graph for this solenoid, taking this as the origin, taking the middle one as the reference point, this is the middle of the solenoid, center of the solenoid. Inside it magnetic field is 0. Then at the end of the solenoid it decreases like this. From the end of the solenoid, magnetic field decreases like this. This is the magnetic field and this is the distance from center. So this is plus the whole length of the solenoid plus L by 2 means capital L, if capital L is the whole length of the solenoid, this is minus L by 2. Inside it magnetic field is constant, but just outside the solenoid, at the end of the solenoid, it becomes half. The graph will be like this. So this is application number 2 of Ampere's circuital law. Now we go to the application number 3 of Ampere's circuital law, the last application of Ampere's circuital law. That is application number 3, and that is toroid. Toroid now we'll discuss. Application number 3, that is toroid. What is toroid? You bring a spring means solenoid, join its two ends. If you join the two ends, what it becomes? Toroid. You join the two ends of the spring, then it becomes a toroid. Toroid is also called as toroidal solenoid. In some questions, some books will find toroidal. Don't confuse when the word comes solenoid. Toroidal solenoid means that is toroid. Its two ends are joined. So it's a magnet having no pole. From where the pole will come? In a solenoid at the two ends there are two poles. One side is north pole, one side is south pole. But when you join the two ends of the solenoid, now the two poles coincide. So it is a magnet having no pole. Remember, when the question comes, can you tell an example of a magnet having no pole? Yes, that is toroid, is the magnet having no pole. So see, I am drawing now the figure of the toroid. So this is suppose the core of the toroid. See the core of the toroid. This is the core on which the toroid wire. Now I'll insert the toroid wire like this. See, this is the toroid wire. I'll turn it like this. Okay. See the toroid. It is now on over it. Current pass. Current enters and current comes out. Now it is visible to all of you. So this is the toroid. And current now is entering like this. So this side enter and this side comes out. This side enter and this side comes out. So here current enters and here comes out. So if enters and comes out, how will the magnetic field lines? The magnetic field lines in this will be closed loop because the two ends will join. So magnetic lines in solenoid is uniform, straight line. But in toroid, when you bend the solenoid and make it a circle, now, the lines of forces also bend and join. So here, if the current is like this passing, so the magnetic lines of forces will be in this direction. This is the direction of magnetic field, magnetic lines of forces. Current is passing like this. Okay. So this is about the toroid. We'll find magnetic field. Let's take the radius of this toroid as capital R. Average radius. As it is inner radius, outer radius, average radius of the toroid capital R. Total number of turns here is fixed, capital M. Total number of turns I have taken capital M. You don't count the number of turns. I am just taking a parameter for it, that is capital M. We'll find the magnetic field in the space enclosed by a toroid, inside the toroid, outside the toroid. Let's find. First you find the magnetic field inside the toroid. You take a point here, P, add a distance smaller, choose 1 ampere and loop, and so first case 1, space enclosed by the toroid, space enclosed by the toroid. So using Ampere's circuital law, B dot dl mu naught I in. What is the current enclosed inside the loop? Is there any current enclosed by the loop? There is no current. If there is no current, so this is 0. So magnetic field in the space enclosed by the toroid is 0. Now let's come inside the toroid. Inside the toroid. So we'll choose the Amperian loop. The Amperian loop will be like this. Will be like this blue line. Let's choose an Amperian loop because we will take a point P here. Let's take the point P here. This is just like this blue line, R radius. This R capital R radius itself. Capital R radius itself is the distance. Okay, this is our Amperian loop. This blue line. If this is the Amperian loop, now use Ampere's circuital law. B dot dl mu naught I in. So B dl. So this angle is 0 cos 0 mu naught. But I in is how much? That is important, you see. So if this is this blue line is the Amperian loop, you see current goes inside here once, then comes out outside, then again enter inside. I am showing you, if this is the ampere loop, current enters here. See, at this point current enters. Okay, by cross sign I show the symbol, and outside it comes out. This is also the symbolic presentation of this toroid. And here again enter, again coming out, again enter, again coming out here, again enter. So every time current enters inside it, but when it comes out out of the loop. You just recall, I have told you one situation like this. Just before I told you one situation like this. Current pass like this, again going outside when it comes, in this situation. How many times it passed? 3 times, 1, 2, 3. But outside what current is going, that doesn't matter for us. So these currents, outside it comes, again enter, again comes out, enter, comes out, enter, always enter in the loop. And how many times it enter? N times, because n number of turns are there. So this is n times current, same current, but if it n times enters, we have to take ni. So angle is 0 again here, so b constant, again outside, dl integration is 2 pi r, so it is mu naught ni. So b is equal to mu naught ni by 2 pi r. What is n by 2 pi r? N by 2 pi r. This is n for small, n number of turns per unit length. Total number of turns divided by total length. The whole circumference is the total length, so it will be written as mu naught ni. This is the magnetic field inside the toroid. Same as a solenoid. Obviously it will be, because just you turn the solenoid and make it a toroid. So this is mu naught ni. But if we come outside the toroid, case 3. Now if we come outside the toroid, you see what happens. Outside the toroid, here we take points are here. You choose the ampere loop. Ampere loop will be like this. Choose the ampere loop. What happens? This is now our ampere loop. This dotted blue line is our ampere loop. If dotted blue line is our ampere loop, we'll use ampere circuital law there. B dot dl mu naught I in. What is the value of I in here? This dotted blue line. Current enter. This dotted blue line. This is our radius r. This is our toroid. This is toroid line. Okay. But ampere line is this one. Ampere line encloses the toroid completely. So here enter. Here comes out. Enter comes out. Enter comes out. Enter comes out. So inside the ampere loop it enter, again inside the ampere loop it comes out. Current cancel, again here cancel, again here cancel, again here cancel. Enter, again comes out, but this all things happens inside the ampere loop. So net current will be 0. Mu naught I will be 0. If I am 0, then what is the magnetic field? 0 inside the toroid. So this is about the magnetic field inside the toroid and outside the toroid, and the space also enclosed inside it. But if the toroid contains some material, some magnetic material having relative permeability mu r, then the expression will be here mu naught mu r ni. Mu naught mu r. What is mu r? This is relative magnetic permeability. Just play the same role of your epsilon r or dielectric constant. This is relative electric permeability. This is relative magnetic permeability. You just recall 1 by 4 pi epsilon naught is the formula for vacuum. But for any medium when it comes, it becomes 1 by 4 pi epsilon naught k, or k, that same symbol is also presented by epsilon r. Epsilon in vacuum. But in other medium it becomes epsilon into epsilon r. The same thing, mu naught for vacuum. For other medium it becomes mu naught mu r. If the material, if the toroid contain any core instead of a vacuum. Also solenoid, the same thing also happens for solenoid. If in solenoid, if you take any core, then also mu naught will be replaced by mu r. So today we discussed Ampere's circuital law and the applications of Ampere's circuital law, thick conductor, solenoid and toroid. Thank you.